All right, so welcome everybody. In this particular session, we are going to go over the list of topics and then stop and work some problems as we go. I have a few requests that were sent to me from some WebAssign and then also from some of our Desmos activities that we're going to look at and go through as we hit some of our topics. So one thing I noticed, just a couple typos on here, we had reordered the units a little bit, but this is actually test 4. Today I realized my pencil, I forgot to charge it. So I'm going to be using my fingers, so things may be a little bit off as I write on the iPad screen. Not as accurate today. But let's go ahead and go over these points one by one. Your unit test will cover 5.1 through 5.5. Keep in mind 5.1 and 5.2 are kind of grouped together with those identities. 5.3 is on equations. 5.4 is on our sum and difference, which is kind of, in my mind, grouped together with our double angle trig formulas in 5.5. So I kind of think about it as 3 main topics that we're going to hit that everything else falls under: the identities, equations, and then double angles, essentially, or multiple angles, you could say. So as far as resources, just like your other tests, Desmos calculator is fine. Handheld calculators, Graphing Scientific are also fine. Desmos should be the only thing that you're using. And then just like for test 3, you can use a note card up to 4x6 with any information you would like. So important on here is to think about the identities that you want to include. Let's go ahead and take a look at our first topic. Our first topic, this is the first topic that I pulled off of our list of topics posted on Blackboard. I can go back and show you where that is when we switch over to a web page. But that has 8 topics, and I just pulled them out one by one so we could do a little bit of exploring these deeper. So our first one was to know your trig identities, listed on page 348. So any of these trig identities that you don't feel like you know, put on your note card. In particular, the requests that were sent to me were to go over ones involving the cofunction, like changing sine to cosine, or secant to cosecant, tangent to cotangent, etc. So the ones we're going to focus on, some of our examples are these ones. But through a lot of the things we go over and do, we'll also see the Pythagorean identities. We may see a little bit of the even and odd as well. All right, so let's go ahead, go back here, and let me give an example. One of the ones that I had picked to look at here. So one of the ones, and I'm going to do it up top here, was in your WebAssign, and the identity was cosine, or the expression was cosine squared, it actually had a bracket, of pi over 2 minus x over cosine. And in particular, note that the bottom is just cosine x, whereas the top is cosine squared of pi over 2, or pi over 2 minus x. So in particular, whenever you see the pi over 2 minus x, that particular phase shift, that is going to be your clue to use the cofunction identities. Now, if we wanted to make it a little bit more complicated, we're not actually going to see this on our unit test. You could see things that have like an x minus pi over 2, and then you might have to think about flipping the sign or pulling out a negative and then using the even and odd in conjunction. That would kind of be like next level identities. I don't think you have any like that, but anytime you see the pi over 2 minus x, or potentially x minus pi over 2, that's going to be utilizing our cofunction. Now, in particular, when we see this cosine squared and then our bracket, I want you to think about this as that is allowing you to also think that that's cosine pi over 2 minus x, and then move the squared on the outside. It's really saying do the cosine of that and then square it. So when we're thinking about transforming using our cofunction identities, think about cosine as your inner function and squaring as your outer function, almost like we're doing a sequence and doing composition. So notice if we go ahead and pull that squared out and ignore it, we can go ahead and use our cofunction identity to rewrite that first part as directly sine of x. So all of this gets replaced with sine of x. And then notice we still have all of that squared. And then we have not gotten rid of that divided by cosine. So we want to incorporate that back in. And then if we think about this one, it helps me, especially when I have exponents, to write out the copies if I'm going to do any cancellation. So let me just kind of come down here. Might be a little bit overkill, but go ahead and write out sine of x times sine of x over cosine x. This allows me to say, hey, that's tangent of x, and then I've got sine of x. Now, as far as this one, there's nothing else I'm going to be able to do with that to go further, so I would probably just leave it there. Notice that in this particular case, sine x times tangent x is the same thing as sine squared x over cosine x. The big thing in this one was that cofunction identity. So any questions on this one? Now, most commonly, you're going to see the sine to cosine or cosine to sine. I think we have a few where we do the secant to cosecant or tangent to cotangent cofunction identities. Let's take a look at one more. Actually, I have two more with the cofunction. So what I'm going to do is just get rid of this stuff really quickly. So maybe it'll just clear that page. There we go. And let's take a look at another one. So for this one, we are supposed to simplify. Make sure I get this right here, that I copied it correctly. Cotangent of x minus cosecant squared of x. Oh, sorry guys, wrong one here. Let me back up. We will do that one in a second. The one I want us to look at with cofunction is sine of pi over 2 minus x times the cosecant of x. So for this one, let's focus on that cofunction identity. For this one, notice we already have it set up with that pi over 2 minus x again. So we should be able to very quickly just switch this over to cosine x. And then we still need to keep the times the cosecant. But maybe instead of going ahead and writing cosecant, let's go ahead and write cosecant as 1 over the sine. So using our reciprocal identity this time. And then if we think about combining these, notice we're just creating a chain of equalities. Like we're simplifying the expression. So if I want to, I can just kind of go over cosine over sine. That's our cotangent. So using the definition of cotangent or the quotient identities. So this guy. So a lot of these you probably already have memorized when we're getting down to taking that expression to cotangent. So questions on this one? Okay, let's take a look at one more. The last one that I want to look at was a similar idea, but it was actually in the 5.2 section, and it said to verify the identity. So let me write that out. They wanted us to verify that cosine of t times secant of pi over 2 minus t is equal to cotangent of t. So in this particular one, the thing that stands out to me first is that cofunction identity. Again, I just pulled ones specifically with those so we can kind of drill down. And this one, notice, is set up so that we can go ahead and change our secant to cosecant. Now, if you think about the idea of this one, 1 over cosine and 1 over sine. So it's kind of like you're still doing a sine to cosine, but embedded with the reciprocals. So let's go ahead and change this guy to cosecant. and we're going to be cosecant just of t. And in this case, with an identity, what I'm going to do is, and it's what your WebAssign would actually have you do in this one, it's going to have you just focus on simplifying the left-hand side, and then on the right-hand side, it's going to have equal cotangent, equal cotangent, equal cotangent the whole way down. So if I think about just isolating and working on that left side, I'm just going to bring down my cosine. And now I have cosine t times cosecant. Now at this point, very similar to the last one, I'm going to go ahead and take care of that reciprocal identity next. So instead of cosecant, let's make it 1 over sine. And then once we put that together, we have cosine t over sine t, which is our cotangent. And notice that that matches with what we were supposed to be getting on the other side. So I think this one in particular was set up as a fill in the blank identity on your WebAssign. All right, so hopefully that helps with some of those verify identities. Other ones that were more requested for the verified identities, in addition to the cofunction, were also ones that were dealing more with cosecants, secants, cotangents, rather than just ones that focus on sine and cosine. So before I go on to a new one, any questions on this one to drop into our box or to ask? Okay, so let's take a look at another one. So the one that I want to look at next, this is the one that I started writing before, we're going to look at simplifying the expression. So just simplify cotangent of x minus cosecant of x squared, or cosecant squared x, over cotangent. Okay, so terrible handwriting there. Hopefully you can read that. And what I would focus on first is anything that I can do with this second piece. Okay, so it might even be helpful to just kind of pull that piece out and work with it so that we can stick it back in and not have to write as much. So let's pull that piece down here. And I'm just gonna go ahead and think about this as cosecant x squared. And maybe even backing that up for a second. And if I think about this as cosecant squared, I could even write it cosecant times cosecant over cotangent. Now, in this particular case, I would probably tackle this by going ahead and getting rid of all reciprocal identities by flipping them. So this one is a little bit strange in that if you have cosecant, and think about this identity, you could write cosecant as 1 over sine. Right, so we have a reciprocal identity, but we already have a fraction. So we might as well go ahead and start moving things around. So I'm going to go ahead and write that one, and I'm going to suppress the 1. So I can go ahead and write that as sine on the bottom. And then since I have 2 copies, notice I have my other copy here, then that's going to end up being another copy multiplied on the bottom. Now, why am I leaving them as 2 copies instead of sine squared? Well, I'm hoping that I'm going to be able to cancel some things later and get rid of that, or get rid of one of them potentially. So let's go ahead and do the same thing for the cotangent. Now, the cotangent one is maybe a little bit trickier to look at because we don't have anything where we have 1 over cotangent. But what we do know is that if you have cotangent, that's 1 over the tangent. And if you think about manipulating this guy, that means if you do, well, let's reverse that. If you do 1 over cotangent, that's going to give you the tangent. In other words, if you flip this side and flip the other side, you're creating another reciprocal. So if you think about this particular piece having cotangent on the bottom, that's going to give us a tangent of x moving to the top. Now, is it the only way to do it? No, right? But again, probably what I would do if I looked at it, get rid of all the reciprocals by moving them. Then I would go ahead and think, this is tangent, which is really sine over cosine. But instead of writing it as a separate piece, maybe let's take this and break it up as sine, and then I'm going to have a cosine drop to the bottom. So we are still kind of changing this one little piece, and we need to keep our minus part up top. So let me try to squeeze this in. Our tangent will replace with sine over cosine. So notice if you do that, the cosine is really going to go to the bottom. And then I'm going to be able to cancel one of those signs. Right? So if I think about what I have here, now I just have a 1 on top. I don't have anything, so there's an understood 1. I canceled one of my signs, but I still have sine of x and cosine of x on the bottom. Okay, so questions here so far. Let's walk back through it. It's not looking like I would expect it to look, kind of looking back at my cotangent. So we want to make sure we didn't make a small error or do anything wrong here. So looking at our cosecant squared, we wrote that as cosecant times cosecant over cotangent. And then we moved our cosecants as our 1 over sines. So we have 2 copies of those. And then our tangent. Okay, and then we did sine over cosine. One of our sines canceled. And let's see here. We took our cosine to the bottom. Okay, so that looks good. So let's go ahead and put that piece in. And we're going to replace our entire red piece up here with all of that. Now, keep in mind, at the very beginning, we still had cotangent of x. And let's think about big picture. Let's say you are simplifying this on a test and you're going, okay, now I don't see anything. I wonder if I messed it up. We're going to keep going, right? Because there may be some things that I can do with this. In particular, I'm thinking about getting a common denominator and trying to combine these two and see if anything cleans up. But if you get to some point and you don't know what to do, we've talked about dropping in Desmos and just checking visually that what we have lines up. Let's do that. Particularly like this one wasn't quite what I was expecting. So I'm going to share, let's see, I don't think I have a blank Desmos screen open yet. Let me do that. And let's type in the original identity and then we'll type in our simplified version. So we've got cotangent of x. Notice we've got that very similar to the tangent with all of our asymptotes. And then for our next part, I've got cosecant squared of x over cotangent. Okay, so that was interesting. We've got all of that stuck in. And then let's go ahead and do the tangent of x. Sine of x, cosine of x. And notice we're getting a Okay, it wants us to be a little more careful here. So let's do this. We really mean when we see those errors, it's saying, hey, I didn't know what you wanted as the argument. Now, notice on this particular picture that everything lines up. Okay, now it was really interesting on this one that when I took away this part, this graph actually almost lines up with a cotangent graph in general. It's almost like a shift of a cotangent. So let's keep going. Okay, in other words, very similar in shape. Okay. All right, so what this tells me is even though it maybe wasn't what I was expecting, we're good to proceed. So let's go back. I'm going to stop this share and reshare on the iPad. And what I'm going to do is get rid of our scratch work for that first piece down here. And then we're going to see if we can simplify our subtraction piece anymore. All right, so let's go for the idea of going ahead and breaking apart our cotangent. So our cotangent, if we rewrite it, we're going to rewrite it as cosine over sine. Okay, so all of this piece is what I'm going to be working with. So cosine x over sine of x. And then we have the reciprocal of the product sine x cosine x. So at this point, I could go ahead and say, well, to get a common denominator, and again, this may get us nowhere. Sometimes with the trig functions, you end up with something that doesn't look a lot better. But the only thing I would really recommend trying is going ahead and saying, all right, you've got cosine on the bottom here. And in order to get a common denominator, I would want to multiply the top and bottom of this one by cosine. So let's do that. It's a little messy here. But if I do that, now the top is going to be cosine squared, and the bottom of our left-hand piece and our right-hand piece is going to be sine x cosine x. So I'm going to go ahead and write that with one denominator. Okay, that means we're going to be able to combine, and then our top is going to be cosine squared. Okay, so again, not a lot better here necessarily, but notice that I can now think about a Pythagorean identity. In other words, we're kind of starting off with something that was a subtraction with cotangent and cosecant, and we're ending up with something that looks like a subtraction with sines and cosines. So let's think about our Pythagorean identities. If I look at this guy and I see that I have cosine squared x minus 1, if I manipulate my Pythagorean identity, let's take it over here, and I want to see cosine u minus 1, I'm moving the 1 over. So I'm subtracting the 1, and then I need to subtract the sine. Or I should have been a little more careful. Sine squared. I'll put a u instead of an x here. So what that tells me is if I go ahead and subtract 1, then I'm going to get negative sine squared u that I can replace all of this piece with. Okay, so we're finally getting somewhere. Let's go ahead. I'm going to do this part. Forgot to add in extra slides, extra blank slides, and I don't want to lose what we had here. So let's just go ahead and write it down up here. So now I have negative sine squared u. Oh, sorry, x. Should put an x back here, not a u at that point. So sine squared, I would prefer they not give us u's, just give us x's. But sine squared x on top, and then negative sine squared x on top, and sine x cosine x. So if we now simplify that expression, then this is going to give us, we can cancel one of those signs, and I'm going to get negative sine over cosine. And then this is going to give me negative tangent. Now, one of the reasons that our graphs look so familiar is now we can kind of think about that tangent and reversing it, and maybe we see that connection. Now, are there potentially faster ways to do this one? Maybe, right? And likely, because this felt kind of long. And this is our longest one so far. But what we want to keep doing is keep breaking apart with your reciprocal. There was no cofunction on this one. At some point, we identified a Pythagorean one that came into play. Without identifying that one, this would have been hard to complete or hard to simplify. Let's go ahead and switch back over to Desmos and make sure that negative tangent matches up with our other graphs. Okay, so we already know that those two pieces match. Okay, and negative tangent does match. All right, so questions on this one. I think one good question is, well, what happens if you're taking the test and you're simplifying an identity and you get somewhere along the process, but not to this point? Like, let's say you got to cosine squared x minus 1 over sine x cosine x and didn't know where to go, and you put that in as your final answer. Now on WebAssign, when it grades it, it's not going to give you any points potentially if it's not to where they want it. But when I go in and manually grade those, I'm going to be looking at what you write and assigning partial credit. In other words, you would get a fair amount of partial credit, even though you didn't identify the Pythagorean identity. So I briefly want to talk about one other before I get rid of this one and clear it out. Questions here. Okay, so the last one that I want to mention in this particular section with the 5.1 and 5.2 is one like cosecant to the 4th of x minus cotangent to the 4th of x. The key on this one is you want to think about a difference of squares factorization. If you think about this as really like a y to the 4th, something to the 4th, minus x to the 4th scenario, you're going to be able to factor difference of squares once. Y squared minus x squared, y squared plus x squared, and then you're going to be able to break down the y squared minus x squared with another difference of squares. So if you keep on doing difference of squares factorization here, I would do it with your x's and y's and then substitute your cosecants and cotangents. So what they're wanting you to do is an expansion. You're not going to see a lot of cancellation in this one. All right, so let's go ahead and go on to our second objective. And this one actually ties in with one of the ones in double angle. So given a particular trig value, for example, if sine of x is 3/5, for example, then can you find the other 6? We've done this a whole bunch of times on other tests, and we're going to do it with a double angle. So I'm not going to do a particular one of this, but just for reference. Usually, if I tell you something like this, I also need to specify what quadrant. So in this case, if we were in quadrant 1, could you find all the others? And the key in this one is to use your Pythagorean identity to go after cosine. And once you know sine and cosine, you can find tangent, and then you can use all your reciprocal. So let's go ahead and take a look at this one. This one I actually kind of did already. When I listed that first objective, knowing those ones, I kind of group them with that, knowing them and using them. In other words, where you're going to see that. But that's technically this third objective. Just recap: simplify and verify trig expressions, including a correct step. Okay, so on your WebAssign or on your test, you're going to see very similar to how your homework is formatted. In other words, there's not a lot of like writing out that step. You saw that more in your Desmos activities. So you can think about, in this case, really focus on the simplify and verify part. All right, this one actually came out a little bit strange. It blew up my text here. But what it said, if you go back to that list of topics, is to solve a trig equation and then write out a solution. So it's basically solve a trig equation where we either have factoring, quadratic, just anything going on. So trig equations. And then write a solution that's between 0 and 2 pi, and then a general solution. Now, all the questions I got for the trig equations were ones involving double angles. So I'm going to go ahead and go on to our next objective. Notice this one. Again, I'm not sure what happened with my fonts here, but solve a trig equation where the angular speed is faster or slower than just your base. In other words, where the b value is not 1. So where we have something like sine of 2x or cosine of 2x. So the request on this particular one also had to do with a few of our Desmos activities. They tied in there. So let's take a look at one together, and then we'll go to our break and come back and look at the ones with Desmos. So in this particular one, let's say they tell us as the given part of the information that the cosine of u is negative 15 over 17. And let's say they also tell you that your angle is between pi over 2 and pi. Now, why do they have to tell you that part? They're telling you the quadrant, because if you think about your cosine, the cosine being negative is going to put you either in quadrant 2 or quadrant 3. Okay, but what they're doing is limiting you that you are going to be quadrant 2. Now, in this particular case, you have a couple of options. If I were working this one, I might say, hey, if I know how to find cosine, I can find sine. If I know sine, I know tangent. But that's going to tell me sine of u and tangent of u. What the actual question went on to ask was, find sine of 2u, cosine 2u, and tangent of 2u. Okay, so I'm just going to focus on sine and cosine. If we have time, we'll get back to tangent. But it was basically not just the singles, but the doubles. And in this particular case, what we have to think about is maybe the most efficient approach. Yes, I could find sine of u using Pythagorean. I could also look at my double angle formulas and think ahead on what's going to be best. So have those double angle formulas for sure written down on your note card. The ones that I would recommend, since you've got space, go ahead and put the 1 for sine double angle and then put all 3 for cosine. So sine of 2u is going to be 2 sine u cosine u. And I think on mine here, I started off with just a single one and then ended up working out for my cosine double angle. So kind of the one I always remember is the cosine squared u minus sine squared u. So this isn't bad. This kind of helps us think about a strategy. It tells me if I can go ahead and find the piece sine of u, then I could plug that piece in here. I know my cosine piece, and that allows me to find sine of 2u. So it's almost like a mini problem where we've got to go back to our original part. In other words, we have to go back to given a trig value, find the other 6, or calculate all 6, the other 5 to get to all 6. All right, so let's think about how we could find this. In other words, let's focus on sine u. So what I want you to think about is drawing your picture and just drawing your reference angle. We know we're in quadrant 2, and we know the cosine is negative. But if we focus on the reference angle, That's going to be this piece. Maybe we could call it u prime, because our u is going to be our large angle. And if we think about in this one, the sine of u is going to match the sine of u prime, because the y value on this piece is also the y value, terrible circle, if you're looking at your larger angle. The sine is positive on both of those angles. So let's go ahead and just focus on the reference angle piece. If this is our u prime, think about your cosine. Cosine is adjacent over hypotenuse. So adjacent is going to be 15, hypotenuse is going to be 17. We're dropping that negative with the reference angle. And then in this particular case, we would want to use the Pythagorean theorem. You're going to see a lot of special right triangles. So this one is actually an 8, 15, 17. If it's not one you know, use Pythagorean theorem, find that missing side. Your special right triangles might be something nice to include on your note card so that you don't have to redo that calculation and risk getting it wrong. Because you could have some that involve some radicals. So if we get 8, then that tells me the sine of u, which is equal to the sine of u prime, is going to be 8 over 17. So in this particular case, now if I wanted to find cosine of 2u, I can go ahead and drop in 2 times 8 over 17 times negative 15 over 17. Okay, so let's go ahead and do that one. And then from that, you could go for your cosine of 2u. So using your double angle, notice we're going to get some large numbers here. It's not going to be pretty. Just go ahead and multiply it out. You're really not going to have to worry about simplifying that fraction. Most likely for most of these, you're just going to have large numbers. Okay, so you multiply it out and you are done. Now, what would I do for cosine of 2u? I would probably go ahead and plug in directly to this piece. If I had cosine squared, that means I'm plugging in and squaring negative 15 over 17. That's going to give me a positive, and I'm squaring 8 over 17, and I'm subtracting. Okay, we're already going to have a common denominator with the squaring, so it's not going to be too bad. Then, instead of using tangent double angle, once you find sine of 2u, cosine of 2u, then you can go ahead and divide. So I would advocate against using your tangent double angle formula. All right, so we are almost out of time for this one. What I'm going to do is go ahead and have us go to break. We'll come back at 10:50. If there's any questions on this one, we'll kind of pick up there, and then we will look at some double angle issues on our Desmos activities. All right, so I'm going to go ahead and stop my share. Tune back in at 10:50 if you are live, and I will see you guys then.